So we're going to start by thinking about the life cycle of stars, and then we'll have a look at the diagram because it makes more sense that way. So basically, the life cycle of the star depends on how big it is. So bigger stars, they burn brighter and they die quicker and they die more spectacularly. And we're going to have a look at some really cool pictures of them, or you can do that yourself. But I'll chuck some at the end of the slides here, so you can have a look at them. And if you ever get to go out and use a telescope, a big one, then you should go do that because it's really cool. And like, you won't see it in the detail that you see it in the images, but you can still see some cool stuff. So you can still see nebulae and you can see like supernova remnants, but they're going to be like, you know, smaller, like kind of fainter. And like a lot of the pictures that you'll see in these slides, they're actually produced in colors other than like the visible spectrum, so they don't actually look like that in real life. They might be picking up like UV light or something. Okay, so first of all, let's start with small to medium-sized stars. So that includes our sun. So we already know that they start off as a protostar. Well, they start off as a nebula, really, so like a big cloud of gas and dust. And we know from our earlier work that actually that dust and gas is a remnant from the previous generation of stars. So that comes together under gravity. It starts spinning. You get that central ball coming in as a sphere because that's just the most stable configuration. And you get that accretionary disk around it. And as it starts contracting more, it spins and then it starts nuclear fusion. And at that point, it's called a main sequence star. So here that's shown as a small star, and that's equivalent to our sun. Okay, so what happens to that star eventually? So it's going to run out of hydrogen gas to be burning. It's going to, basically exhaust its fuel in the core. And so when that happens, and it was in hydrostatic equilibrium, remember? So it had that gravitational push going in and it had the fusion push coming out. When there's no longer any fusion push, the gravity wins that contest, and the core will actually collapse. And as the core collapses, the outer layers actually blow off, and they cool down. And as they cool, they turn like a red color. Remember from our spectral classes that red stars are cooler than yellow stars. So basically these are a cooler, redder outside section, but the center is still quite hot. Sorry, we'll wait for a second. Enough, Lisa. Okay. So basically our star is now a red giant. So these things actually turn helium into carbon, and like in their core. So we're thinking about our CNO cycle now. We're starting to see that sort of stuff. So basically, we'll be turning the helium into carbon, and then basically when it runs out of that, it's just going to basically collapse again because there's no fusion pressure pushing out. The core becomes a white dwarf, which is a very small star that's actually quite hot, but it doesn't look very bright because it's just tiny. And the outer layers become like a planetary nebula, so like a really cool, beautiful cloud.